All right, welcome back. Today is the first day of the actual new material in Computer Science 3. That's CSCE 310. This is the summer session. Today we're going to be starting to talk about brute force algorithms. And today we're going to focus mostly on generating combinations, combinatorial objects called combinations. But before we do that, let's motivate why we want to look at brute force algorithms to begin with. Remember that we are on Piazza, so if you have any questions during the live Q&A, I'm not able to look at the YouTube comments, so if you are enrolled, make sure that you are asking questions on Piazza during the in the live Q&A thread. Brute force algorithms basically are not, in general, not a great solution. That is, they're not really efficient, because they involve looking or generating every single possible solution. You generate or examine every possible solution to find the A solution or the best solution to a problem. All right? So, unfortunately, there are lots of solutions. The solution space could be huge. It could be exponential. It could be super exponential in the case of, say, permutations, where you're generating every single possible arrangement of n elements, which leads to n factorial number of permutations. Imagine a standard deck of playing cards, where you've got 52 cards, and you shuffle it up. How many possible arrangement or how many possible shuffles are there? It's huge. 52 factorial is bigger than the atoms in the known universe, or whatever you want to compare it to. But certainly you're not going to be able to go through every single permutation, every single shuffle to examine what's the probability of pulling two pairs. Right? You need a much better solution than that. That's where mathematics comes in. But for small input sizes, say only five permutations, that's only what, 120 things that you have to examine. But as we've already seen, even n-squared algorithms, n-squared solution spaces are not at all practical for even moderately large data, right? But why do we still look through it, right? Often generating or creating a brute force solution helps you to understand the problem, right? And look for structure to exploit, right? And we're going to see that, we're going to witness that here today. Data structures and algorithms. Why do we like data structures? Because we like structure. Why do we like structure? It's because we can exploit that structure. If you can examine a problem and see that, well, I don't actually have to look at every single possible solution. I can rule out all like half of the possible solutions over here, right? You've already cut down your solution space in half, right? If you can find it even more of a structure and say that, well, I can cut it down from an exponentially sized solution space down to simply just, a linear amount of solution space that I have to examine. Now you've got an efficient algorithm to solve this problem, to tackle this problem, right? Often such approaches require generating combinatorial objects, right? For example, finding the closest pair, right? We already did this in the first lecture, where we created a brute force solution, straightforward solution. Just generate every single possible pair of points and find the closest pair of them, right? We already saw that that's inefficient for even moderately large data. If you have a million points, then you're then you are ending up going with a million times a million squared, whatever that happens to be, possible solutions, and it's going to take minutes, hours, days, centuries, even for moderately large data. N squared is not acceptable, right? But with finding the closest pair, what were we doing? We were generating combinations of size 2, right? In other words, another way of looking at that is that we were generating subsets of size 2 of a set of size, say, n, right? Where we had n points originally. My LaTeX is still not working, so That's one thing I forgot to check out. But one thing that I am testing today, and looks like it's working already, is that I will be able to use my iPad for writing notes instead of the low rent overhead projector kind of style here. Let's go ahead and start by checking out how to. Yep, everything seems to be working still. Let me just check on YouTube to make sure that it works. All right. Hopefully this will work. All right, good. As a first step here, let's remind ourselves really quickly here, say from 235, that is discrete math, or often, at least in the United States, you are exposed to combinations and permutations in the 7th grade or so, 6th or 7th grade. So what is a combination, first of all? A combination is an unordered, so order does not matter, subset of a set. And just to illustrate by example here, suppose that we had the set A, B, and C. Right? What are all the possible subsets of that set of size 3? Right? Well, we have the singleton sets, sets consisting only of one element, A, B, and C. Right? We also have, you can call them doubletons, or what we were doing yesterday, we were creating pairs, right? So you can pair up A with B, you can pair up A with C, and you can pair up B with C. Right? So there are 3 of them here, there are 3 of them here. Why didn't I pair up B with A? Remember, again, they are unordered. Order does not matter. So A, B is the same thing as B, A, right? And you don't have to worry about that, right? So we're missing a couple more here. There are actually going to be 8 subsets in this case. The one where we include everything. In other words, the original set itself. But I also left some room up here because we are forgetting the empty set. The empty set is the set containing no elements. That's always going to be a subset of any set, right? That's a tautology. It's always going to be true. Okay. So how can we generate these things? Well, yesterday we were only interested in these guys right here, where we have A, B, A, C, B, C, or in other words, pairs. How did we do that? We did that with 2 for loops, right? For I running ... for J running ... Right? Now imagine that we had a much larger set, a set of size 20 elements, and we wanted to generate all triples, right? There would be a lot more than just one here, but the naive approach would be simply, well, if you want to generate all triples, then what would you do? For I, for J, for K, right? ... Right? In other words, it would lead to an n squared, or n cubed, excuse me, algorithm. Up here it was order n squared. Right? If you wanted to generate all combinations of size 4, then that naturally is going to lead to a n to the 4 complexity. Right? But you'd have to hard code these things if you took this following approach, where you are creating all triples. All right, that's 3 for loops. All elements of size 4, okay, that's all 4 loop. That's 4 for loops, right? Et cetera, et cetera. You don't generally want to do that. Instead, you want to think of a solution that will solve it generally for everything. The one that I usually teach in 235, it's been a long time since I've done 235, but it's a very simple one where if you want to generate all subsets, you can just simply do counting, right? The way that works, I'm not going to go through the full details, but the way that it works is by simply associating your set with a binary string and then iterating through all binary strings. So what I'm going to do is I'm going to start out with a binary string of length 3, right? 0, 0, 0. Right? Make sure everything's working. Actually, let me check YouTube to make sure everything's working. Okay, good. We are on a delay, but that's okay. 0, 0, 1. So I'm just counting in binary here. This in decimal, this of course would be 0. In decimal, this would be 1. 0, 1, 0, that's going to be 2. 0, 1, 1, that's going to be 3. 1, 0, 0, 1, 0, 1. I'm just counting. I'm going in order here. 1, 1, 0, and then I end at 1, 1, 1. And you'll note here that I counted from 0 to 7. In other words, I generated 8 binary strings. How many elements were over here again? 1, 2, and then 4, 7, 8. So how does that give us a way to generate all possible subsets? What I do is I associate each one of these bits with an element in the set. So A, B, and C. If it's 0, that means that the element is not included. If it's 1, then it's just the opposite. The element is included. All right? So what do each one of these bit strings correspond to with respect to this set over here? Well, 0A is not included. 0B is not included. C is not included. That's the empty set. Nothing's included. Likewise, if you jump all the way down to the end here, 1 means that it is included, is included, is included. That means that we are looking at the set A, B, C. Right? So you can imagine what it looks like now. That it's not in the same order that I wrote it before. I just naturally over here, I wrote everything in lexicographic order, A, B, C. A comes before B, B comes before C. But over here, it's not going to be lexicographic, which is fine if you resign yourself to generating every single possible subset anyway. A is not included, B is not included, but C is. So that corresponds to the singleton set C. This corresponds to the singleton set B. And this is going to be B, C, because A is not included, B is, C is. Likewise, the rest of them. A, there's that singleton set for A. Another doubleton here, or a pair, A and C. And then finally, A and B. And you can check that we've gotten all the sets that I already enumerated over here. Right? That's an easy way of generating every single possible subset. All you have to do is start at 0, go up to, in general, 2 to the n minus 1, right? For 0 up to 2 to the n minus 1. Convert, I'll call this I to binary, and generate the subset. By simply just iterating over each one of these bit strings. Go to the first one, second one, third one, right? And you add it or you don't add it depending on whether or not it's a 0 or a 1, right? That's if you have to generate every single possible subset. What if I'm only interested, like I said in like we did yesterday, I'm only interested in the doubletons, in the pairs, right? Then you're doing a lot of superfluous work here, right? Here, so there's our first structure that we can kind of exploit. That I don't need to generate every single possible subset if I'm only interested in triples or I'm only interested in pairs. But I also don't want to go back over here to the old way of doing it, where I just hard code a bunch of for loops, right? Before we get to that, though, the algorithm to do this, what I want to do is I want to, darn it. Oh, I want to do a little bit of analysis, right? And observations. If I generate all subsets, how many of them are there? Well, you're generating basically the power set. The power set, then how many possibilities there are? Well, it kind of hints out here where we count. We're counting from 0 up to 2 to the n minus 1. And if we include 0 in that, then we end up getting 2 to the n. In other words, exponential. And that's not even acceptable for even small input sizes. Small input sizes, even here being, say, 50 or 60 or something like that, then generating every single possibility, it's doable. But if you get up to, say, 100, now you're talking about getting it done by the heat death of the known universe or something, on a computer at least, on today's computers. So that's not at all a good solution if you're only interested in combinations, right? Remember, the number of combinations is n choose k, which has you can expand this out to n factorial over n minus k factorial in the denominator, right? This is the number of subsets of size k, right? Or in other words, k combinations. Remember, everything is still unordered. We haven't talked about permutations at all yet. Subsets are inherently, or sets are inherently unordered. How many of them are there? Let's just check if there are any questions for now. Nope. A lot less chatter today, too. Oh, well. All right, so, well, we've already looked at, one instance where we've got n choose 2. Well, that's going to be n times n minus 1 all over 2. And if you just, do big O analysis, look at the highest order term there, that's going to be order n squared, right? If you do n choose 3, right? Well, we did that kind of over here by hinting at using 3 for loops and saying that it's going to be order n cubed, right? Well, that's the same, right? N times n minus 1 times n minus 2 all over. Basically what we're doing here is a bunch of these are canceling a bunch of these, and so we're only left with 3 left on top. This goes away. And this is going to be 3 factorial, which is, of course, 6, right? And if you look at the highest order term here, you've got an n times an n times an n times an n, and then a bunch of lower order terms. Then this is going to be order n cubed. In general, n choose k is going to end up being order n to the k. Hey, that's polynomial. Great, right? Well, we've already observed that even if you get up to the polynomial of degree 2, then for all practical purposes, for large data, it's not going to work, right? It's not going to be practical. You're going to want to look for much better solutions. But not only that, you can go to the middle of this, right? These are binomial coefficients, so they're symmetric, right? They go down. Over here, we've got 1, 3, 3, 1. So they meet in the middle here, right? And if you, jump to the middle, right, where you have n choose n divided by 2, this is not at all polynomial. In fact, this is exponential. Right. So if you consider k to be a constant, then yeah, you're kind of deluding yourself into thinking that this is going to be efficient. But yeah, it is going to be a polynomial. But in general, it's not polynomial. If k is not a constant, then you're right back to exponential, right? If you generate, if you have a set of size 100, and you want to generate all subsets of size 50, right, half as much, then you're looking at an exponential amount of work to do that, right? And it's probably not at all going to be feasible, right? Nevertheless, we should be able to develop an algorithm for this, okay? And at this point, I'm going to go back to my notes here, right? And let's start talking about how to generate combinations, right? All right. Let me make sure that it is working. If it's never not working, please post in Piazza, and I'll try to troubleshoot on the fly here. But otherwise, I'm much happier now. 0 dropped frames, and I can use my iPad now. I had to cut a whole bunch of stuff down and then use a separate computer over here to say do Piazza and error checking on YouTube. Right? So here's the algorithm. Suppose that you are given a set of n elements. Oops. 1, 2, 3, 4, ... and then up to n. Right? Now, I've labeled them as numbers here. When I was working on the iPod, I labeled them as letters, A, B, C. Right? It doesn't really matter what it is. It could be a set of people, right? And then you've got John and Jane and Anna, etc., Alice and Bob, right? And you want to take a subset of them to form a committee or something like that. It doesn't matter. This algorithm that I'm going to show you is going to work for any type of set, because what you can do is you can use these numbers as indices, right? So if you've got your set of people and you've got 5 people, just associate numbers with them. Bob is 0, Anna is 1, John is 3, etc., etc. Chris is 4, and Joe is 5, right? And now all you need to do is generate combinations of indices and then map that back to each one of these people, and you've generated a subset of people instead of a subset of numbers. So given a set of elements 1 through n, and note here that I am using 1 indexing as far as the pseudocode is going to be concerned. But when we actually go to program this as a demonstration, we'll of course want to use 0 indexing because that's what most programming languages use, right? So here's my outline. You start with the identity the identity k combination. So you start out with 1, 2, 3 k, right? And then you assume that you have elements A1, and unfortunately it's not going to typeset that well, A2 ... AK. Right. I wonder why it's not. Okay, nope. Still not working. We want to generate the next k combination. Right. So what we do is we locate the last element, a sub I, such that a sub I is not equal, and unfortunately I'm not going to be, I'm going to use code kind of syntax here instead of LaTeX syntax. N minus k plus I, right? And we're going to call that a sub I. Now, before we go on here, let me remark that we start out with 1, 2, 3 ... up to k. Then we jump into the middle of the algorithm. Somewhere in the middle of the algorithm, we've got these elements. We're not going to call them 1, 2, 5, 7 or something like that. We're going to just give them labels, A1 through AK, okay? And we want to generate the next k combination. So we're going to locate, we're going to start at the end, and we're going to work our way forward. So even though combinations are unordered, while we're generating them, we're going to impose an ordering on them so that we can actually iterate over them in a consistent manner. But ultimately, it won't matter because combinations are unordered, right? So we're going to locate the last element, a sub I, the last being from the right, such that this inequality does not, the inequality holds, the equality does not hold. Okay? And then what we're going to do is we're going to replace a sub I with a sub I plus 1. If a sub I, that's just a variable, if it holds a value of 5, in other words, we're just going to increment it to 6. Okay? And then we're going to replace each a sub j, so I've got a different iterator variable now, with a sub I plus j minus I for all j running from I plus 1, excuse me, up to k. Okay, so there's our outline, right? And what I'm going to do, it's not necessary to understand that immediately. Let's just go ahead and go with an example, okay? And for that, I'm going to go back to my iPad over here. Right? So, again, we start out with, actually, let me go ahead and choose n to be 5 and k to be 3. And so we've got a set here called 1, 2, 3, 4, and 5. And we want to generate all combinations of 3 elements, okay? So normally we would start out with 1, 2, 3. Right? The next one would be 1, 2, 4, 1, 2, 5, ... I'm going to jump into the middle of the algorithm to where it actually, I didn't show the details of that. I'm just going to jump into the middle of the algorithm where something interesting, it becomes more interesting. So suppose that we are at 1, 4, 5, right? That's our combination. We want to generate the next one, Okay? So in other words, A1, A2, and A3 are 1, 4, and 5 respectively. Okay? So we start. That's what we assume. We have A1, A2, A3, and then we want to generate the next K combination. What we need to do is we need to locate the last element. So we're going to work from the right all the way forward, such that find last element, such that st a sub I is not equal to n minus k plus I. Right? So that's our first step. Let's go ahead and do that. I'm going to start at the end here and start examining these things. So a sub 3 is equal to 5. And I'm just going to put a question mark here. Is it equal or not equal to the right-hand side here that I've set up? In other words, n minus k plus I. Right. So let's start filling these things in. N and k are always going to be fixed. So 5 minus 3, right? 5 and 3. And then plus I. Well, I here is the index value that we're looking at. Right? We're looking. Well, it'll be 3, then 2, then 1, until we find something where this inequality holds. Right? So in this case, it's going to be 3. Right? That's equal 5. And so they are equal, and the inequality does not hold. Right? We want to find the last one that is not equal. So we go one more, right? Go to the next one, right? From the right, we're working down. A2 is equal to 4. Question mark. Is that equal to n minus k plus I? Right? Question mark. Is it 5 minus 3 plus... Now, in this case, I is 2, right? Because I've changed my index value right here. Well, hopefully you can see immediately that that is, in fact, equal to 4, right? So that's not the thing that we're looking for. A1 is equal to 1. And is that equal to 5 minus 3? And in this case, I'm just going to skip right to the end here, 1. Right? 5 minus 3 is going to be 2 plus 1 is equal to 3. And so they are not equal. And consequently, a sub 1 is the thing that we're looking for. That's the last element such that that inequality does not hold. So what do we found what we're looking for. What we need to do now, if you want to look back at the notes here, is that we need to replace a sub I with a sub I plus 1, then replace all the elements after it with those values. Right? So replace a sub 1 with a sub 1 plus 1. Well, a sub 1 is 1, so if we just add 1 to it, then a sub 1 becomes 2. Right? Then we replace a sub j with a sub j. There we go. A sub I, right? Plus j minus I, for j running from I plus 1 up to and including k. Remember, we're using 0 indexing here, so we're actually going to go up to an inclusive. In other words, this is the thing that ended up giving us the inequality. So we change that to 2, and then we proceed to go back to all the elements that are above it. So we worked initially from the right down to the left to find that element. Now what we're going to do, we change that element, and then we work right. Right? In other words, A2, we replace that with a sub I plus j minus I. Now let me fill those things in. What is a sub I? Remember, a sub I, the thing that gave us this this replacement, was a sub 1. So that's going to end up being a sub 1. J, here in this case, it's going to be 2, because I'm iterating over j is I plus 1, I plus 2, dot, 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 all the way up to k. In other words, it's that index value right there. And then finally, I, well, that's going to be 1, right? Because a sub 1 is the thing that gave me this replacement. Right? A sub 1 consequently was already replaced, and so that new value is what we use. Right? So it'll be 2 plus 2 minus 1 equals 3. So A2 becomes 3. I don't have enough room here. Oh, let me do it over here so that I don't have to go to the next page. A sub 3 will be replaced with a sub I plus j minus I. Remember, a lot of these things don't change. This is going to be 2, and I is always going to be 1 for every single one of these iterations, plus j, in this case, is 3. That's the only thing that changes. So that's 5 minus 1. It's going to be 4. So we've got 3. Oh, sorry. That wasn't what it was replaced with. We've got 2, 3, 4 as our next combination. Oops. 2, 3, 4. And in fact, these are going to be generating the combinations in lexicographic order. You're going to start with 1, 2, 3, 4, then or 1, 2, 3, 1, 2, 3, 4, 1, 2, 5. It's kind of like counting, right? And that's basically what the algorithm is. It's just counting in a different kind of base system, and then but also skipping some things. Okay. So what I want to do now is one thing that a lot of people have problems with is taking pseudocode and translating it directly into, say, regular old code. So before we do that, let's actually write the pseudocode for this. And of course, you can find this in the book, or at least in my lecture notes. But so suppose that we're given as input a combination, and I'll just call it C equals A1, A2, dot, 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 AK, right? So this is only doing one iteration. It's only giving us, here's one combination, give me the next combination. It's not actually doing all combinations. For that, you need some master for loop that iterates until you're done. By the way, how do you know when you're done, right? When there is no such element that inequality holds. You're starting at the end. That's not it. 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 Oh, okay. There's no other element, so I'm done. I've generated the last combination. That is the last combination. There's no more to generate there. So we're gonna have to keep that in mind when we actually program this. Okay. All right. All right. So that's the K combination of n elements. And our output is going to be the next lexicographic K combo. All right. So I'm going to do exactly what we did over here. I'm going to start at the end. First of all, we need to find the thing that we're replacing. I'm going to start at the end and work my way over here, as long as this inequality does not hold, right? So I need an initialization variable. I'll go with I. I start at the end. Remember, K is the end right here. So I start at the end, and I go down, I go down, I go down until I find the thing that I'm looking for. I don't know how many iterations I'll have to use, so I'm going to naturally use a while loop to do this. While this combination, this inequality does not hold. In other words, just write this inequality, but make it an equality, right? While a sub I is equal to n minus k plus I. Right? Just making sure I've got it correct. I will decrement I. Once I've broken out of this while loop, that means I've found the thing that I'm looking for. That I now represents that element that I need to replace. So let's replace it. A sub I will be replaced with a sub I plus 1. Right? Just like we did over here. I've scribbled it out here, but it was 1 before, and then it became 2. Right? And now what we need to do is we need to work the other way. So here I'm going to just use a regular old for loop. And then I used j before, so j running from I plus 1 up to and including k. I'll replace a sub j with, oops, be consistent about it here. A sub I minus j plus I. And that's it. And then output a sub, well, the new a sub 1 through a sub k. Right? Now I've skipped a lot of details because of course this is pseudocode, right? If I gave you a list or an array representing a combination, then are you gonna modify my list, or are you gonna create a new one, or what, right? So that's the kind of question that you have to ask when you actually go to program something like this. For that, let's go ahead and do it in Python, right? Just to get some Python practice here. You'll see that I've imported a package or a library called copy, because what I'm going to do is I'm going to ultimately create a new copy. Right? So first of all, let's just go ahead and make and create. I'm just going to cut and paste this. Some test code here. All right. So let me walk you through this. N is going to be 5. K is going to be 3. So I've got a set of 5. 0, 1, 2, 3, 4. Right. And that's what I've done. Well, I haven't done that yet here. But then we're going to want to generate subsets of size 3, right? So A, B, C, D, E. I want to generate ABC. I want to generate ADB, right? All triples basically, right? And we'll see if this actually works, right? I'm going to print out the combination that I start with. The combination that I start with here is I'm doing a range, so 0 up to k, but not including k. So 0, 1, if k here is 3, this is going to end up being 0, 1, and 2. I have to wrap it in this list call. If you're not familiar with Python, a range is just an iterator. It's not going to be an actual list, an array. So I'm going to have to force it to become a list so that I can hand it off to the function that I'm about to write here. Right? We'll ignore the rest of that for stuff down there until we've actually got something to work with. So I'm going to go ahead and create a new function. Oops, sorry. I'll call it next, right? Because that's what I called it down below. We're going to have to take in a combination and n. In the pseudocode, we took a combination, and implicitly we took n because we're saying that there are n elements, 0 through n minus 1 through n in the pseudocode. Here it's going to be 1 through n minus 1. Okay. Let's go back to the pseudocode and see what we should do first, right? So we should iterate through the elements starting at the end until we find an element that needs to be replaced. Okay. So I'm going to just simply start a loop here. Right? K. First of all, I need my k. I need n and k to work with here. That's going to be the length of the combo list that we've been given. Len is short for length. Again, if you're not familiar with Python, that gives you the size of the list. Okay. So again, 0, 1, 2. We start out with that. That's going to be of size 3 because there are 3 elements in there. I'm going to initialize I to be the length of the. Well, actually, I've already got it. K minus 1, right? Yeah, there we go. In the pseudocode, we set I to be k, but that's because it was 1 indexed. I'm going to correct for that by going down and starting at the last element. Remember, there are 3 elements in here, so they're indexed 0, 1, 2. So I start at 2 here. There are 3 minus 1. That gets me to the end. All right? And here's my while loop. While the result of I, and I've introduced a new variable here on purpose, equals n minus k plus I. Then I will decrement I. So now 2 things here. First of all, I have not created this variable yet here. Like I said with the when we were looking at the pseudocode, you have to when you actually translate that to code, you have to be thinking about how code actually works. In Python, lists are passed by a reference. So any changes that you make to that list are going to be reflected in the calling function. Maybe we don't want to do that. Maybe we want to create here. I'm going to give you a combination, and I expect a brand new list that represents the next combination. I don't want you screwing up my my original list. In that case, that's why I brought in this copy library or package or whatever you want to call it. I'm going to go ahead and create a result that is a copy. In fact, it's a deep copy of the combo. I'm never going to touch the combo. I'm only going to create a result. This creates a completely new deep copy. If there is 1, 2, 3 in it before, now it'll there's a 1, 2, 3 in this result over here. And so I'm only looking at the result, and I'm only changing the result. The second thing that I would draw your attention to is that this is very common in a lot of programming languages. It's the decrement operator, right? You'll find immediately that you can't do this in Python. It does not have the decrement operator. So you actually need to use be more pseudocodey kind of by explicitly saying I is equal to I minus 1. Right? Okay. Now, the result. Now what I need to do is I replace a sub I with a sub I plus 1. That's just going to be result of I is equal to result. And again, I can't go plus plus either. So I'm going to have to go with result of sub I plus 1. Okay. Going back, what else do we do now? Let me go ahead and highlight this. Sorry. There we go. Now we can actually just almost directly translate this for loop into Python if you want to. It's going to be for, and I'll use the same variable here, j, running from I plus 1 up to k. Now, of course, that's not Python yet. I want to run from I plus 1 all the way up to and including, not including k, because, of course, 0 indexing now. We're going to stop 1 short here. We can get that, as I introduced to you yesterday, with range. We'll start at I plus 1 and go up to k exclusive. So that gives us exactly what we want. Right? Result sub j is equal to result sub j plus j minus I. Remember that that was the... oops. Ooh. I didn't mean to do that. There we go. Remember that that was the expression that was given in this algorithm here. Okay. So going back over here, I, of course, do need to return... actually, I'm going to leave it like this for a second, okay? Because it is a scripting language. It's not compiled. There are transpilers and compilers for Python that can check for certain things. And linter, and more accurately, what you want is a linter here, because I've not actually returned anything. Now let's focus on this for loop down here. I'm just running it for 20 iterations here. I'm giving it the combination that I'm replacing that variable reference with whatever combination I get back, and I print it out. Note here that I did print it out before I actually started this so that we can see that identity k combination. Let's go ahead and run this with Python 3. Oops, good. Sorry. That is syntactically incorrect. You can't make an assignment variable in a for loop. For j in the range. There we go. Oh, still a problem here. Oh, okay, that's why. So we started out okay, 0, 1, 2. That was the original list over here. We printed that out. But the very first time that we did this, it failed, right? Why? It's not telling us what the actual problem is here. On line 5, taking the length of a none object, what does that mean? So let's go over to 5 here. So this is just hand wavy kind of debugging here. We came into this method with a combo that happened to be none, and we asked for the length here, right? Actually, that was happening in the second iteration. Oh yeah, that was happening in the second iteration because we did successfully print out the identity combination over here on line 17. We did get a combination back, and then we printed it. But what was it? It wasn't the next combination. It was none. And that's a very common error. I do that all the time. You fail to return anything. I actually want to return the result here. Right? And when I return, before, when there was no return statement, it was simply doing the default of returning, oh, there's nothing to return, so here's nothing. And then you print it out, none. That's what, and then you give none to the next combination on the second iteration, and it ends up dying because it can't take the length of none, right? The length of none is not 0 in Python. So let's go ahead and see this in action now that I've fixed it, right? 0, 1, 2, 0, 1, 3, 0, 1, 4, right? And then we've exhausted everything because it's only 0 through n minus 1, 0 through 5. And so we have to increment this next one, 0, 2, 3, 0, 2, 3, 4, dot, 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 dot. Right? And you get the idea here. Oops, I think that there is a problem because we definitely should not be... oh, you know what? 5 and 3, how many are there? Right? Let's 5, choose 3. Let me go ahead and compute that. 5, choose 3, 10. There should only be 10 of them. And so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Even that one's screwed up. I've got a bug here somewhere. If you see it, great, tell me. Otherwise, I'm going to look at my the code that I've already done, I plus 1. Oh, you know what? I don't think that we... nope. I minus 1. Results of I is equal to results. You replace that for j in range of I plus 1 up to k. Oh, duh. I never actually changed anything here. Results of j, I stopped typing, plus j minus I. There we go. That'll work a lot better. I still want to go up 20 iterations here to show you what I'm talking about. Nope, that's still wrong. Oh, you know what? Yep, there. Well, let's go ahead and consult our pseudocode again here. So you got to pay attention to indices. There is I here, that's j, and then that's I. So I, j, I. Going back over to my code. Now it's been fixed. Before it was j, I, j, and then I. Okay? So now it should work, but of course it will go off the deep end. So let's go ahead and try it again. And the first 10 iterations are going to be all valid, right? And if you write out all the combinations of A, B, C, D, and then map them to 0 through 4, you'll find that those 10 combinations are correct. Now we start getting into incorrect combinations down here because of the design of the way of our method here, right? There's got to be an end. Where do you end? Well, here we ended at the last combination, the lexicographically last combination, 2, 3, 4. After that, this will never be satisfied, right? While that result, it's not throwing an index out of what's ending up happening is that the index is going out of bounds. It's going from all the way down to 0 and then minus 1. But Python's not throwing an index out of bounds exception here because it's looking at this and evaluating it to false, I believe, jumping out of the while loop and then continuing and giving us garbage results, right? So what I want to do is I want to check here to see, did we fall off the deep end? If I is less than 0, then that means that there are no further combinations. Return. Now here in this case, I'm just going to return what the default was before. Return none. Right? And when we run this, we'll see that. Oops, sorry. Oh, it should return none. Oh, you know what? We give it none, and then same thing that happened at the beginning. We return none, and then we give it back none. None. In which case we can't take this length here. So just as a simple exceptional case here, we'll do some error checking. If the combo is none, you can. I don't think that you can do this. Right? You can't say equal equals. In any case, it's more idiomatic to do is none. Right? So if combo is none, return none. Don't even bother with the algorithm. Right? And that way we won't get that traceback exception. We'll just get none, 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 none. There, you gave me the last combination. There are none to give, so I'm going to give back none. And then we end up giving it none again. There are no other combinations, so I give you back none. And you can see that there are 10 valid combinations here, and after that we have none, 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 none. Right? Okay. Any questions online? How did you get the n value and the k value here, or do you assign those? I just created it. Right? If you want a different combination, if you want subsets of size 5 from a set of size 10. So if you have 10 things and you want all subsets of size 5, that's where those numbers come in. Now this is, I don't know how many there are, but there's certainly way more than 20. But we can look at the first 20, right? In which case, 0, 1, 2, 3, 4, 0, 1, 2, 3, 5, dot, 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 all the way up to and including 9, because of course n is 10, right? If we wanted to change this to a little bit better loop here, while combo is not none, then just keep going. Give me all the combinations here, right? And we initially printed out the first one. Of course, I can change that print statement there. But this one will end up doing them all, right? If we change the print statement, it'll be a little bit cleaner. If we put the print statement at the top. Now, let me kill all that and run it again. We start out with 0, 1, 2, 3, 4, all the way down to 5, 6, 7, 8, 9, the last 5 elements in the set. Right? So I just made them up, right? If you want different values than representing different sets and different sized subsets, then you can easily change these. This one will be easy to see what I mean here. What this is taking a set of size 10, and I want all singleton sets because k is 1, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? If you want everything, all subsets of size 10, well, there's only one, the set itself, 0 through 9, right? Okay. Okay. So I want to show you another way of doing this because it leads into our first actual problem that we're going to solve with this stuff. And for that, I'm going to go back over here to my iPad, right? All right, there's another way of doing this using recursion. So what we just did, both of the solutions that I just gave you were iterative. And in general, I'm not a fan of recursion, but it does lend itself to a problem-solving approach called backtracking, which, again, falls under brute force. So here's the idea, at least with sets. In fact, start out with the empty set. And suppose here that the set S is equal to A, B, C, D. We want to generate all subsets. Right? So we're back to generating all subsets, not just pairs or triples or K combinations. Okay. Well, if I start out with the empty set, I've got a few choices. I'm going to build the next set. I can add A, or I could add B, or I could add C, or I could add D. So let's explore all 4 of those possibilities by branching out here. Suppose that I add A. Right? Then that leads to the singleton set A. Suppose that I add B. That leads to the singleton set B. And suppose I add C. That leads to the singleton set C. And finally, I add D. And that leads to the singleton set D. Now let's examine just one of these branches here. I started out with the empty set, and I said, okay, well, let's go ahead and add A. And this is the set that I have now. Now I've got some choices. First of all, sets are unique elements, so I'm not going to consider adding A again. And I'm not going to consider these branches over here. I'll consider those later. I still now have B, C, and D. I have 3 choices. I can add B, or I could add C, or I could add D. So let's branch out in each one of those choices. If I add B, then I have A, B. That gives me the pair A, B. If I add C, that gives me AC. And if I add D, that gives me AD. Right? I'm quickly going to run out of room here, unfortunately. I'd love a whiteboard-sized iPad instead. That'd be cool. All right, so again, let's focus on just one of these computational branches. I started out with the empty set. I added A, I added B, and I don't want to add those 2 things again, so I'm going to look at the remaining elements in the set, C and D. I have similar 2 choices. I could add C or I could add D. A, B, C, A, B, D. And again, let's focus simply on one branch at a time. Let's focus down here, A, B, C. I don't want to add those again because of course, unique elements, but I could add D. So, A, B, C, D. And if I'm looking at this as a computational branch of recursion, then I'm down at A, B, and C, and D, and there's nothing else to consider. So I've generated that set. Right? Now let's go back. Right? We're going to backtrack, and we're just going to simply use the recursion to do it for us. I came down this branch. I started with the empty set. I added A. I added a B, and I made the choice to add D. Right? Well, if I look at I'm not going to consider C because I considered that on this branch over here. And looking at D, there's nothing else to consider, so that's a dead end as well. Let's go back up. This choice led me to add A and C, and there's still other things left in the set to consider. So I could add D. Right? And you can see where this is going. There's nothing else here to consider adding, so I'll backtrack, go down here. I added A and D, and I'm not going to consider B and C because I considered that down this branch over here. So I'm done with that branch, and I recurse back up. Right? Now I'm going to recurse down to this choice. I ignored A, I added B, and now I need to consider adding C and or D. So let's branch out there. B, C, and B, D. Right? This branch, if I look ahead here, I've already considered the last element in the set. So I'm not going to go any further. That's a dead end, right? But this branch, I can consider adding D, B, C, and D. There we go. At that point, both of those are dead ends, and I come back up here. And I consider the other choice. Well, what if I had added C instead? I'm not going to consider A and B because I considered those paths down here. I look at the next element, D. I could add D to that set and get C, D. And I'm again at a dead end because there are no further elements. I'm at a dead end over here because by adding just D and ignoring the first three, I'm not actually ignoring them, I'm just considering them in different branches over here. Then I've produced every single possible subset in this scenario, right? All you need to do is count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? There are 16 nodes, you can say here, right? I started out with a set of size 4, and I needed to generate every single possible subset. How many of them are there? 2 to the 4, 16. All of them are represented here somewhere, okay? Why is this going to be a useful approach when we look at this tomorrow for backtracking? It's going to be because this is a computational tree like I called it before. And if you've got a tree that's too big, especially here in Omaha, we have many trees below over. What should you do? You should prune them, right? By cutting, like if you looked ahead and said, you know what, I'm going to exploit some structure here. I don't need to examine this entire subtree because I know that all of these solutions are going to be infeasible or no better than the solution that I've already produced. That means that I can cut that out, right? And if you've got this very large exponentially sized tree like we have here, and you can start pruning out and cutting out branches, then you can make your tree much, much smaller. We'll learn how to do that tomorrow. For now, though, what I want to do is I want to get some more practice and actually implement this in Python. Okay. So I'm going to call this function, and I'm not going to go over the pseudocode because that's in the book. But I'm going to, and we don't have enough time today. But I'm going to call this function subsets. Right? It's going to be a recursive function. I'm going to give it a set A, B, C, D. And I'm also going to give it an intermediary subset, right? That's going to be like these sets that we produced as we went along here, right? That I'm going to start out with the empty set, and I'm going to hand that off to a recursive call. But I've also handed this off as well as n if you really want to. Okay. Remember that throughout this algorithm, though, when I was at this node, AB is my current subset. I want to consider what else should I add? I need to know, well, what have I already considered, right? Because sometimes you jump to the you're somewhere in the middle, right? What you want to do is I've considered A, B here. I need to know that C and D are still a possibility. So what I'm going to do is I'm also going to give it an index, right, to keep track of that. Right? So let's go back over here, and that my index choice here is just going to be J, right? So let's write this out in a little bit of comments here. Set is the overall set of elements. Right? Subset is the intermediate subset of elements, right? And J is the index for the other elements we're going to consider. Okay? So bear with me here. First of all, we need an n, right? So n is just going to be the length of the set, right? And we also need a stopping point here, right? Well, let's go back over to the diagram, right? Where did we stopped here, we stopped here. We knew each one of these leaves in this computational tree was a dead end. Why? Well, if you look at the common theme here, what's at the dead end of each of these? D, 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 D. In other words, if there's nothing else to consider, right? If the index that you're tracking here has already fallen off the edge of of the main set here. Right? So in other words, if J is n, there are no more elements to consider. So we return and do nothing. Otherwise, what we're going to do is we're going to look at all the other elements J and or beyond J, right? If we have A, B like before, I want to consider C, D. So J is representing B here, right? I want to look at J plus 1, J plus 2, J plus 3, and consider adding each one of those elements. So that's going to be a simple for loop for K in range of we start at J plus 1 and go up to but not including N. Right? And that's why I needed N there. Right? So I will add set sub K to the subset and recurse. Right? So my subset here, subset of, actually subset.append, I'm just going to throw it out at the end. Set of K. Right? And then I'm going to make and let's print it out so that we can actually see what we're doing here, subset, right? If you're actually using this to solve a problem, here's a subset, do what you're going to do with it, right? Is it a feasible solution? That subset maps back to your actual problem of whatever you're trying to solve, and then make your determination, oh yeah, that's a good solution, or that's an infeasible solution, ignore it, right? And then I will make a recursive call here, subsets of set, the same subset, and then K, we don't want to pass, sorry, it is going to be K, because we add A, B, C, D, E. We're here. Add C, but we don't want to consider C again because we've already added it. So, go to the next index, right? Which is going to be K. Right? And there. So now consider the recursion. Let me go back to my diagram here. Right? Consider the recursion again. And let me restore this right here. Right? We're going to go down, we add A. We're going to go down, we add B. We're going to go down, we add C. We're going to go down, we add D. When I come back up, I don't want D to remain in that set. So or more accurately, over here, I'm going to add C, and then I'm going to add D, but I don't want C over here either, right? So after I recurse back up, if I've added C, I want to take it away for my next recursive call down to the other side, right? So as a next step, after the recursion, I'm going to take that out. And in Python, to remove the last element is just simply a pop. Lists are kind of treated as stacks, so you can push things on. I don't think they actually have a push method. Instead, it's just append, but you can treat it as the same. Subset.pop. That removes and returns, I believe, the last element in there. Right? And that's it. That's all we need to do. We do need to initialize this and set it up, though. I don't know if I can. Can I go? Nope. Yeah, yes, I can. I can do block comments so that doesn't print out anymore. All right. What I need to do is I need to call this subset here like I did over here. How did I start out? I started out with the empty set. So let's create a empty set. So and a set. Set will be simply just a list of a range of, say, 10, of n. I'll use the same n up here. I don't want to do 10 because that would be 2 to the 10. Let's do what we were doing in our example 4, right? So instead of A, B, C, D, it'll be 0, 1, 2, 3, 0, 1, 2, 3, right? And my subset here is going to be an initially empty set, or a list in this case, and that's just going to be the square brackets. And my initial index variable here is going to be -1, and I'm going to explain that in a second here. And now let's call subsets of set, subset, and index. And let's see what we get here. Hey, there's all the sets that we were looking at before. 0, A, AB, ABC, ABCD, and then we backtracked. Right? We came out of the recursion, removed the last element, removed that last the 2, so that we could go down and explore. Well, what happens when we add 3? Right? We were actually coming back up here. We removed the 2, and then we added the 3 back in. That's going to be AC, ACD, AD, and then the rest of the branching. Very last one here is just simply going to be D. Right? All right. So why did I start out at -1 here? Look again how it works. We iterate over the range of j plus 1 through n. So if we have an empty set, what have we considered so far? Nothing. Right? So 0, 1, 2, 3, we need to start our index variable before the list even starts. And so that's going to end up being -1. Right? Of course, you can take care of that in the function itself, and then you could start out at 0 over here instead. And I believe that the biggest change would be that you you don't go +1 instead. Right? Okay. Let's double check any questions online. None. Okay. That's generating subsets. And again, why would you want to do it recursively when recursion is in general bad? It's because it lends itself to a problem-solving approach, a brute force problem-solving approach called backtracking. To understand that, though, we need an actual problem to work with. I'm going to take a problem from your homework called the 0-1 knapsack. My iPad is... Okay. My iPad is working well enough that I'm going to go ahead and write it down over here instead of the notes. Not well enough. I don't know if it is getting choppy. Let me know. I don't know if the throughput is getting choppy or if it's just locally choppy. It hasn't dropped too much, 4.2% of the frames. But in any case, let me go ahead and give you the statement of the problem, and that's where we'll end today. We'll talk about how to approach the problem tomorrow, because of course you will be programming something like this. All right, so where is subset? Nope. Where's my 0-1 knapsack? Maybe it's the first one. Sorry, bear with me here. Sat. And I should have had this up. There we go. All right. So here's the problem. It's called the 0-1 knapsack problem. A knapsack is just a bag, right? It's a bag that you carry things in. 0-1 refers to, and as we'll see here in a second, that you can take an item or not take an item. Usually, this is given given in the context of, say that you're a robber and you've got a knapsack. You break into a store. You want to fill up your sack with valuable items, right? You want to, gold or whatever, but you can't carry, 1,000 pounds of gold. Your knapsack only holds so much. You want to steal the most valuable stuff to fill up your knapsack, but you want to make sure that you can carry it out so that you actually get away. And so the 0-1 knapsack problem is usually stated in those terms, that you're a robber. If you want to think about it in different terms, where I don't know, the store is on fire and you're saving the most valuable things instead because it's your store, right? And now you're no longer a robber, right? So here's the actual problem. Given a collection of items, A1 through AN, right, with weights W1 through WN and values V1 through VN. So these all these items, they weigh something. They all have value. So you can immediately rule out corner cases like something that doesn't weigh anything, or something that weighs a negative, like helium. Helium's pretty valuable, but you have to put it in a balloon for it to be weightless. But they're each WI and VI, VJ, these are all going to be greater than 0. Because if you have something that has value 0, of course you can immediately throw that out of the problem entirely. If you've got something with a weight of 0, you can immediately put that in your knapsack and not have to worry about weight at all, right? So you can take that out of the problem as well. And a capacity of your knapsack. And I'll call that big W. Yep. So the context here is that we want to output a subset, right, of, and I didn't give this a name, I'll give this a name A. There we go. A subset of A, such that the sum of all the weights, and how do I write this? Of all S in S, of the weight of, of the elements, say S, right, is less than or equal to W. In other words, you've filled up your, you're not exceeding the capacity of your knapsack. You can actually carry this out of the store, and the sum of values in what's in your knapsack is maximized, right? Of course, you could refuse to fill up your knapsack at all, and that's a valid solution. It's not going to exceed your weight capacity, certainly. You're just walking out with an empty bag, but that doesn't have any value, right? You put at least one thing in there, and you can, you can get value out of that. Okay. Let's look at an actual example here. Right. So here's an item. A1, A2, A3, A4. You'll see a theme here. I've chosen to consider subsets of size at most 4, right? Just like we generated all the subsets of the values and the weights. Say the values are 15, 10, 9, 5, and then the weights are 1, 5, 3, 4. Now this is a small enough instance that you might be able to see what the optimal solution is. By the way, I didn't give a weight capacity here. Let's say that we can only carry 8. So if you need to couch these in more concrete terms, say that these are pounds and these are dollars, right? So you can only carry 8 pounds because, I don't know, you had a hard day. You can only carry 8 pounds out of the store. What do you immediately do? Well, if you're greedy about it, you could say, okay, I'll take the most valuable items first. In other words, I'm going to go in order. I will take, let's be greedy. I will take A1, A2, and can I take A3 at that point? Well, remember A1 has a weight of 1, or sorry, a weight of 1. A2 has a weight of 5, at which point I'm carrying 6 pounds. I can only carry 2 more pounds, and A3 here is 3 pounds. That would end up being 3. That would end up being 9 altogether, right? Which is exceeding my weight capacity here. So if I chose to do this, A1, A2, A3. This is an infeasible solution. Okay, fine. Well, I guess I don't really need A3, whatever the hell that is. So let's just go ahead and go with a solution of A1 and A2, because those are the two most valuable things. This says is feasible, and with a weight of 6, as we already computed. But what is the value? Well, if I took the first two items here, 15 and 10, then that means I've got a value of 25. Right? I've gotten away with $25. All right, fine. I'll cut my losses there. Is there a better way? Right? Right? Does anybody see it? What if I had skipped and gone on to, let's see. What if I had skipped the second one? Let's go with A1, A2, and A4. First of all, is that feasible? Am I not exceeding my weight capacity? Well, that's going to be 1, 3, and 4. I am at my weight capacity. 1 plus 3 plus 4, 8. Yes, it is feasible. Okay? What is the value? Now again, I'm going to add that up. The value is 15, 9, and 5, which, if you do the math correctly, it's going to be 29. And that's a much better solution than being greedy about it, right? Unfortunately, if you want to take the naive brute force approach here, it means that you're going to end up generating every single possible subset, even though a lot of those subsets are not going to be feasible, right? This is a small enough example that I'm not going to be able to demonstrate it. But suppose, let's go back to our diagram over here, right? I'm adding elements. At some point, suppose that this is much larger. For example, suppose that I added A. Oops, undo that. Suppose I added A and then immediately adding B makes the entire solution, A, B, infeasible. Why bother considering adding a third or even a fourth element? In other words, I could take this entire tree, this branch of this tree, and trim it out. Right? So once you've filled your knapsack up to capacity, you know, okay, that's a dead end. Remember that solution because it might be valuable, say 25. But now let's go ahead and explore other feasible solutions to see if we can find anything better. Right? And this algorithm that we developed to do this recursively allows us to do that. I'm about to recurse over here. I'm about to recurse over here. And before I do that, right, I ask, is it feasible? If yes, okay, go ahead and explore that. If no, don't even bother going down that branch. And if you've got a much, much larger tree, then that means that you may be cutting out an exponentially sized branch. Right? Now, you're not going to end up cutting it down probably all the way to a polynomial, but you could cut out half or 75% or 90% of all solutions. Right? It's still going to be exponential in general, but heuristically, in practice, that leads to a much better solution if you can get rid of other solutions that you know are not going to be feasible. Right? I will start tomorrow on how you can go about doing that. And then we'll get into other combinatorial problems, generating permutations, etc. Okay? Any last questions? Otherwise, it looked everything looked fine today, at least on my end. Let me know how it went in the Piazza comments because I don't look at the YouTube comments. Okay? All right. Have a great day.